Hi there, my name is Dr. AJ Kumar, PhD. We are doing Abstract Algebra 27. We are reading section 2.7 out of Artin. This is Equivalence, Relations, and Partitions. This is partially a test. I'm testing a new recording setup. So, of course, the first thing we're going to do, we're going to go through in yellow and highlight all of the terms. And then if I don't know a term, I'll maybe highlight it in a different color. Even and odd. I guess we're talking about integers in this context. Let me make the highlighter bigger. Even, odd. Partition, I know what that is. Just kind of glancing at the context. Equivalence relation, I know what that is. I'm not going to highlight those. Double check. Just scanning for italicized terms. Representative element. Inverse image or pre-image is the term I usually use. Fibers. Alright, and that's it. Now we go in blue and highlight the previous prior references. And we aren't going to look them up yet. We'll go do that on a third pass. That's a previous reference in this section. I'm not gonna 258, okay. Alright, let's look up 258. I think that's the only one. This is a list of equivalence so this is page 49. Go buy the book. There's a link to buy the book down in the description. Page 49, there's a this is a list of equivalent conditions for equality of cosets. That's what that is. Alright, let's go back to the beginning. I'm not even going to read the context for that to figure out what it was being cited in. Alright. (2.7) Equivalence, Relations, and Partitions. A fundamental mathematical construction starts with the set S and forms a new set by equating certain elements of S. For instance, we may divide the set of integers into two classes, the even integers and the odd integers. The new set we obtain consists of two elements that should be called even and odd, or in Zmod 2 arithmetic, you call these 0 and 1 respectively. Or it is common to view congruent triangles in the plane as equivalent geometric objects. So, this is what I was talking about with quotienting, where you factor out some group of symmetries that, so what I mean is congruent triangles. Any operation on the plane that maps every triangle to another congruent triangle, let's say, that's a symmetry with respect to the congruence relation on triangles. So what you do is you take the ordinary planar coordinate relationship of equality of triangles and you factor out by that group of symmetries. And then you get Euclidean geometry where you consider so what I was saying, 90% of the difference, is this one of my block quotes? I hope it is. If not, I'll try to remember to add it next time. That 90% of the difference between any two fields of math is in their definition of equals. And in this group theory, particularly this idea of equivalence relations and the subsequent idea of quotienting, is how you go about changing your definition of equals. Or it is common to view congruent triangles in a plane as equivalent geometric objects. This very general procedure arises in several ways that we discuss here. A partition. Now I want to note that there's a conflict between math terminology. There's a conflict between math terminology and computer terminology. So if I take, let's say, let me take a pi, okay, and I'm going to partition it in the verbal sense like this, okay? Okay. Okay, and then I have now three parts. So part 1, part 2, 3, and 4. Okay? In computer language, each of parts 1, 2, 3, 4 is a partition. Oh, oops. And then in math, the way you cut up the... So in computers, a partition is a piece of the pie. That's what partition means. In math, it's the way you cut up the pie. So in math, the set 1, 2, 3, 4, that is your partition. That is your partition. The way you cut up the pie is the partition in math, and in computers, a piece of the pie is the partition. That's an important idea. That's an important difference, namespace collision in the terminology. So, a partition pi of a set S is a subdivision of S into non-overlapping, non-empty subsets. 2.7.1. S is a union of disjoint non-empty subsets. Okay, let me reread this and think about it. A partition pi of a set S is a subdivision of S into non-overlapping. God, my voice. I ate a bunch of carrots and it just has destroyed my voice. I'm not sick, actually. My voice was fine like half an hour ago. I just ate a bunch of carrots. And it's just dried the hell out of my throat. A partition pi of a set S is a subdivision of S into non-overlapping, non-empty subsets. 2.7.1, okay, is a subdivision of S in a non-overlapping, non-empty subset. Okay, so this is what I said. It's a way to cut up the pie. So in computer terminology, a partition is one of those non-overlapping, non-empty sets. Non-overlapping, the normal math term for that is, let me put this in quote, the normal term for this is disjoint or pairwise. The normal term is pairwise disjoint. Pairwise disjoint, non-empty subsets. So S is a union of disjoint non-empty subsets. The two sets, even and odd, partition the set of integers with the usual partition. The two sets, 1, y, xy, x squared y, and x. God, I want to fix my voice. Oh my god. The two sets, even and odd, partition the set of integers with the usual. Why is my voice like this? Why is my voice? Why is my... I don't know. I can't fix my voice right now. I'm sorry. The two sets. There we go. Just let me get some more water. There we go. Let me wash the carrot. Okay, I think that's better. Oh my god. I was like getting such sore throat from okay, if I talk for like 30 seconds it comes back. You know what? I think I sound like Alex Jones, so it's fine. My goal has always been to be the Alex Jones of math. So maybe that'll be my trick, is I eat a bunch of carrots before every time I turn on the recording. And then I'll have the Alex Jones voice. That's Alex Jones' secret, isn't it? Eating fucking carrots. That's why he sounds like this. Oh my god, it's just murder on the throat though. The two sets, even and odd, partition the set of integers with the usual notation. The set's 1, y, x, y, x squared, y, x, x squared. Right, so the usual presentation of S3, I don't remember where that was given, but we've referenced that numerous times before in this playlist. We called it the usual presentation. And I don't remember the number for it of S3, but yeah, you can partition the usual presentation of S3 up into this partition. An equivalence relation on a set S is a relation that, oh my god. An equivalence relation, okay. Oh my god. An equivalence relation on a set S is a relation that holds between... Oh my god, I can talk for like 2 seconds and then it just goes away. Okay, I'm going to power through this. An equivalence relation on a set S is a relation that holds between certain... See, now I hear myself, I sound like Alex Jones, and I'm just laughing. Anyway, an equivalence relation on a set S is a relation that holds between certain pairs of elements of S. We might write it as A tilde B and speak of it as equivalence of A and B. I'm not going to highlight that. An equivalence relation, I've talked about this back in Abstract Algebra 21, I believe, is required to be transitive, symmetric, and reflexive. Right, so transitive means if A is equal to B, B is equal to C, then that implies A is equal to C. Note that these three properties correspond in a very straightforward manner with the group laws. So, what I want you to think about when you have an equivalence relation is I want you to think of the equivalence relation as being given by a group. So, what this transitivity relation is saying is that if I can go from A to B using an element of the group, so a group, think of it as a group of transformations acting on some other set. So go check out. This is a draft right now, but kind of the ideas are there, and I need to write it out, but I just don't have time right now. Revelations 23. That's not a keyword. That's a reference. References will go in curly braces, I guess. Revelations 23. Okay, so if I can go from, there we go. Voice seems to be coming back. If I can go from A to B, and then go from B to C. Oh my god, this is killing my throat. If I can go from A to B, and then from B to C, then I can go from A to C using the group. Okay? That's all we're saying here. That's the typical way in which you are presented with an equivalence relation in mathematics. Is you are given a group, so you're given an ambient set, which I'm going to call, in Revelations 23, I use the term stage, and the group acts on the stage, and what we're going to see is, what I've talked about is that the fundamental idea in math is called quotienting, and right after this we talk about quotienting in Artin, or right after this Artin talks about quotienting. It's amazing how my voice just comes and goes. Okay. Okay. Okay, let me stop talking for like 2 minutes. Okay, so the transitive relation states that if we can go from A to B and B to C, then we can go from A to C. So in other words, let's suppose that we have a transformation that maps element A to element B, and that transformation is called G. And then we can go from element B to element C using a transformation called H. What this transitivity relation means is that H of G, according to function composition, is in the big group. So all this is the closure property. This is the closure property. This is the closure property. This symmetric property is the inverse property. And this one is the inverse property. Let me tell you about that. What this means is that if I can go from A to B using some G, then there's a G inverse that takes me from B back to A. If a reflexive property is the existence of the identity element, meaning there's a transformation that does nothing. Okay, so these equivalence relation properties relate in a very straightforward manner to the group laws. They are in a sense the same rules. So you have your 3 group laws and your 3 equivalence relation laws. They're kind of birds of the same feather. Congruence of triangles is an example of an equivalence relation on the set of triangles. So if A is congruent to B, B is congruent to C, then A is congruent to C, sure. If A is congruent to B, B is congruent to A. Reflexive, every triangle is congruent to itself, yep, okay. Conjugacy is an equivalence relation on a group. 2 group elements are conjugate, A conjugate B, if B is GAG inverse for some group element G. Let's suppose transitivity. This means that B is equal to G1 A, G1 inverse, and C is equal to G2. Right, okay, yeah, you can just combine them like that. Right, exactly. Go read this paragraph. I can just predict it ahead of time because I'm the smartest mathematician who ever lived. The concepts of a partition and an equivalence relation on a set S are logically equivalent, though in practice one may be presented with just one of the two. I didn't know that they were logically equivalent. That's interesting. Yeah, I guess if A is in the same partition of B, and B is in the same partition as C, then A is in the same partition of C. If A is in the same partition as B, or its same part as B, and then B is in the same part of A, and they are equivalent, aren't they? Okay, so an equivalence relation, I can see how a partition determines the equivalence relation. I don't see it the other way. Okay. Yeah, okay, so this one's obvious. Okay. Yes. Given an equivalence relation, one defines a partition this way. The subset that contains A is the set of all elements B, such that A is congruent to B. This is the equivalence class. This is a good, important term that I didn't see when I was scanning. I'm sorry about that. Equivalence class. This is a really, really important term. By the way, my postseason bracket was completely busted in MLB. I thought the Cardinals were going to beat the Dodgers because the Dodgers always choke and the Cardinals always have some devil magic. And the Cardinals gave up a walk-off home run to the Dodgers. Anyway, this is important. Okay. This is the equivalence class of A. We denote it by C sub A here. Right. The next lemma completes the proof of the proposition. Given an equivalence relation on a set S, the subsets of S that are equivalence classes partition S. Okay. This is an important point, so we will check it carefully. Okay. The notation CA stands for a subset defined in a certain way. The partition consists of the subsets, and several notations may describe the same subset. I'm going to underline this. Several notations may describe the same subset. Okay. The reflexive axiom, I'm sure you've seen the axioms meme by now in the slideshow. The reflexive axiom tells us that A is in its equivalence class. Therefore, the class C sub A is non-empty. Okay, so we have a non-empty set S. Okay. So if we have is that part of the definition of equivalence relation? Okay. So there's sort of only one possible partition there's no possible partitions of an empty set, because one of the rules for parts or subsets was that each part has to be non-empty, right? Let's just go look. Yeah, into non-overlapping, non-empty subsets. Okay. That's important. So if there's only one element, there's only one possible partition. Okay. In which case you just trivially have an equivalence relation. Okay. But if you have more than one element, okay, then you pick a C sub A. So you assume that one of them exists. A is in the equivalent, so A is in C sub A. And then A is in the set S by, so we pick an A and S, and A is in C sub A. Okay. Right, and so the union, okay, let me write this as, the union over A in S of C sub A is equal to S. Right? That's what this is saying. Okay. The remaining property of a partition must be verified is that equivalence classes are disjoint. What is the property? Partition. Let's go look up partition again. Right. Okay. Okay, so we have to show... So every subset is non-empty. So we showed that. Then S is the union of the partitions. That's one of the properties. And we have to show that they're pairwise disjoint. That's the next thing. Okay, and that's what he's going to show. If CA and CB have an element in common, then CA equals CB. So this is very similar. This reminds me of 2.5.7, which we just looked at, which was proving that if two cosets, if A is in the what was it? If A is in ZB, then ZA is equal to ZB. If CA and CB have an element, say D in common, right, this is using a divisor argument. Okay. If CA and CB have an element, say D in common, then CB is a subset of CA. That is, any element X of CB is also in CA. If X is in CB, then B is in X. Any element, so we have X in CB. Okay. X is in CB. That implies B is with X. Okay. What are we trying to show again? Equivalence classes are disjoint. Right, okay, so X is in CA and okay. This proof makes sense. Okay. So if CB is a subset of CA, well then you can just swap the roles of A and B and you get that CA is also a subset of CA, so CA is equal to CB. Okay, that makes sense. Okay. For example, the relation on a group defined by A is congruent to B. Okay, I gotta zoom out, I'm sorry. A congruent to B if A and B are elements of the same order. Elements of the same order. So if A is of the same... Okay. Huh. Yeah. Wow. 2.7.2. That's interesting. Okay. That's interesting. Okay. If a partition is given, then we may construct a new set S bar whose elements are the parts of the partition of S. Imagine putting the subsets into separate piles, and now we regard the piles as the elements of our new set S bar. It seems advisable to have a notation to distinguish a subset from the element of the set S bar, the pile that it represents. If U is a subset, we will denote by brackets U the corresponding element of bar S. Thus, if S is a set of integers and if even and odd denote the subsets of even and odd integers respectively, then bar S contains the two elements brackets even and brackets odd. We will use this notation more generally. When we want to regard a subset U of S as an element of a set of subsets of S, we denote it by brackets U. And this is going to conflict with my terminology notation, but fuck you, Artin. When an equivalence relation on S is given, the equivalence classes form a partition, and we obtain a new set S bar whose elements are the... So, let's just quickly recap why the equivalence classes form a partition. So, suppose you have an equivalence relation and you have two right, you can partition it into equivalence classes because of transitivity. Right. So if A is equal to B, B is equal to C, then A is equal to C. So in other words, if two equivalence classes overlap, then they are equal. Right, that was the argument. If two equivalence classes overlap, then they are equal. That was the argument Artin gave. Okay. We can think of the elements of this new set in another way. Yeah, here is what I was saying. Ding, 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 ding. Ding, 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 ding. Changing what we mean by equality. This is what I've been saying all this fucking time. Changing what we mean by equality. How many fucking times have I said this? 90% of the difference between... should be one of the fucking block quotes in the slideshow, and if it's not, I'm going to add it next time. 90% of the difference between any two fields of math is their definition of equals. And more deeply, most of mathematics comes from changing the definition of equals and seeing what happens. And here we see what we mean. As the set obtained by changing what we mean by equality among elements. If A and B are in S, we interpret A tilde B to mean that A and B become equal in S bar because CA is equal to CB. With this way of looking at it, the difference between the two sets S and S bar is that in S bar, changing our definition of equals. This is quotienting. This is what I was talking about. Okay? Is that the difference between the two sets S and S bar is that in S bar, more elements have been declared equal, i.e. equivalent. It seems to me that we often treat congruent triangles... Right, this is what I was saying. Okay, this is what I just said earlier. The congruence relationship among triangles as a group. So if you have a transformation that... Let me just explain this. So if you have, let me just draw two, let me use the ruler. Okay, I'm going to try to draw two congruent triangles. Okay, and then, okay, let me draw it at kind of an angle. Let's pretend that these two are congruent. What I'm saying is that the set of congruence relationships, so a congruence transformation that transforms triangle, let me turn off the ruler. This is triangle A, and this is triangle B. The thing that transforms triangle A into triangle B, that's an invertible transformation. And so, the congruence relationship, you specify a relationship in math, in practice, by specifying all of the transformations that preserve the relationship. That is how you, in practice, specify a relationship, and that's always a group. Okay? So, really what we're viewing is that when we talk about geometry and congruent triangles in school, we take rational 2, or real 2 if you're a modulo the group of congruence relationships. The group of invertible transformations that transforms congruent triangles into more congruent triangles. Okay? That's what we study when we study school geometry and we study triangles and we don't care about the differences between congruent triangles. Okay? For any equivalence relation, this is the fundamental theorem of mathematics that he's hinting at, which is sometimes called the first isomorphism theorem. And he's hinting at it here. Or sometimes the fundamental theorem of homomorphisms. That's what he's hinting at here. Homomorphisms. That's what he's hinting at here. Pi, the word, so it doesn't usually refer to the number. Pi usually means projection, which mean projection and surjection. These are synonyms in math. And I did another video in the past where I talked about what a surjective map is. This means onto in English language terminology. A map is onto if it is a surjection, or if it is surjective, which means it is a projection. Those are synonyms in math. That maps an element A of S to its equivalence class. Pi of A is the class of C, is bracket CA. When we want to regard S bar as a set obtained from S by changing the notion of equality. Changing the notion of equality! How many times have I said this? Changing the definition of equals. God, if that's... okay, I gotta go... Okay. I think I forgot that block quote as one of the block quotes. But I will make sure to add it in the next video. I don't want to go add a block quote in the middle of the video. Okay? But that is... how many times have I used this block quote? I think it's in Revelations 23, all over the place. Here, let me open in Revelations 23, okay? 2:23. It's very rough draft right now. It's not okay. Here we are. Okay, this is 90% of the difference between any two fields of mathematics is in their definition of equals. And in a deeper sense, most of mathematics is just changing the definition of equals and seeing what happens. Dr. A.J. Kumar, PhD, the founder loves you. I say this all the time, and we're talking about it here. Artin is talking about what I talk about all the fucking time. He's talking about it right now, okay? And I will make sure in the next video that is one of the slide block quotes. Okay, I like the slide block quote idea. Then the map pi becomes pi of A is equal to A bar. Right, so what it does is, let's say that you are... Okay, let's give an example. Let me give you a concrete example. We're going to... okay, so from the even to odd thing. So we have pi, our map pi, from Z, to Z mod 2Z. So it maps integers to whether the integer is even or odd. That's what Z mod 2Z is. Go watch the first WFC video if you don't believe me. It's just even versus odd. Okay. So it maps every element, so it would map 17 to the class of 1 in this notation, right? Or equivalently, the class of 1 is equal to the class of 17. Because these two are in the same equivalence class with respect to the group 2Z. So you're taking Z and quotienting out, i.e. changing your notion of equality by saying, I don't care about the difference between... Okay, yeah. I don't care. I am pretend... How do you say it? I am taking my original space, Z, okay, which is the integers, and saying, I am going to consider two elements as being equal if they differ by an even number. So 1 and 17 differ by an even number, i.e. an element of 2Z. 2Z is a group. It's a subgroup of Z, which we saw in the previous, in the subgroups of the additive groups of integers. I think that was 24, video 24. 1 and 17 differ by an even number, i.e., that is, they differ by an element of 2Z. Okay? So, when we talk about Z mod 2Z, we're saying, I am constructing a new space where I am taking the integers, and I am saying, I do not care about the difference between two integers. I am pretending that they are equal, and I can do this in a perfectly mathematically consistent way. I am pretending that they are equal as long as they differ by an even number. And then what you do is you look at the orbits. So let me make this bracket term, and I'm going to try to outline this more clearly and maybe from a less CIA glowy perspective in Revelations 23. Okay, now I'm more motivated to go back and work on Revelations 23 because I think I can make this argument a lot better, a lot more cleanly than Artin can. And it's not as if Artin is dumb. He's one of the greatest mathematicians of the... Well, he's a great mathematician. He comes from a great pedigree. Okay, but I think I can make the argument a little bit more logically sound and a little bit clearer, and that's what I'm going to do in Revelations 23. Okay? And this is called calculus for white people. That's what Revelations 23 is. And the group theory is completely unnecessary in Revelations 23, but I'm mostly doing the group theory so that I have a chance to iron out these arguments myself, the arguments that Artin is making, okay? But maybe that'll have to go on the back burner. I'm not 100% sure. I've also been vlogging me working on Revelations 23, so if you want to go watch that, that's in the Q anal playlist. That's in the Q anal playlist, and Revelations 23 goes well with Revelation 6. And in Q anal 2, I talked about why I decided to write Revelations 23, and it was because of a conversation with Craig Cannon where he got hung up on a specific point, and then I realized, oh, I can tie this question he had, which was a very simple question, and I can use it to talk about 4 years worth of mathematics, because what I can do is, so his question is, why is the derivative of x to the n, why is this nx to the n minus 1? Okay, well I can draw a couple diagrams to show why that's true, and I drew those diagrams. I added them back to Revelation 6, and Revelations 23, I'm like, okay, how do I put... So, the question is... Okay, there's two questions that kind of coincide and turn out to be the same question. Number one, how do you put this idea into a precise, logical... I better be recording with the correct microphone. If I am not, I'm going to lose my shit. It looks like I am recording with the correct microphone. Okay. How do I put this fact into a proper, correct, logically consistent, closed, computable mathematical context? That's the first question of Revelations 23. Question number two, how do you handle situations in math where you only have information up to some... You have, let's say, the results of an experiment, and they have a margin of error to them. How do you handle that in a way that keeps track of the margin of error properly? And my claim is that those two are the same question. Or rather, that those two are different questions that have the same answer. And the answer is to not be a when you're doing calculus. God damn it, now I can't put this on YouTube. But anyway, is to be a white man when you're doing calculus. Okay, that's why it's called calculus for white people. Okay? So, my point was, I can't remember my point. Oh, and then when I was writing this out, I realized, okay, well, in order to talk about this calculus question, you can go back and trace it back to a question just about how to approximate Pauli numbers. So let's backtrace. So this derivative question, so derivative, this traces back, you backtrace this to approximating Pauli numbers. Okay, and this traces back to This derivative question traces back to approximating Pauli numbers, and this traces back, let me write down the time, 23, 29, just so I know when to go back and bleep that. Okay, and roughly about a minute ago, so roughly 23, 28, okay. So derivatives comes back to approximating Pauli numbers, and then this leads to some interesting this comes from an interesting set of combinatorics questions, which can be answered in a very clean and really interesting and straightforward way using group theory. So our path in Revelations 23 is we start with some group theory. We see a bunch of applications of group theory, one of which is answering some very simple questions in combinatorics. These are the questions that you would face in like a discrete math course, which is, you know, how many five-card poker hands are there that have 3 aces? That type of stupid question. Okay? That's a combinatorics question, and you can figure out the answer to that by studying group theory. They're in a sense the same question. Okay. Now, one application of the combinatorics is sort of, or the combinatorics questions relate in a very fundamental way to questions about polynomials, or to questions about Pauli numbers. Okay? And then the Pauli numbers naturally lead to the derivative questions, which is how do you approximate the Pauli numbers. And this is Wildberger's algebraic calculus, basically, by Norman J. Wildberger. Okay? That's what I'm talking about in Revelations 23. But it's actually, I may have bitten off more than I can chew, and I have other things I need to work on. I have actual things that bring me, and so god damn it, 23:31, 23:31. Okay. So I have some actual things that bring me some Semitic metal, and that's more important. And then I have Marketplace, which is really important to me, and I have to prioritize that over Revelations 23. I don't know. I didn't realize how much time I spent writing Revelations. It actually is super time consuming, and programming it seems like I get way more done in less time, which is interesting. Anyway, we can work in S-bar with the symbols used for elements of S, but with bars over them to remind us of the new rule. So sometimes you'll see this in number theory textbooks. When they're talking about, let's say, Z mod 2Z, they use 0 bar and 1 bar. Okay, but eventually you get tired of this notation and you just use 0 and 1. Okay? Okay, if A and B are in S, then A bar equals B bar means that A is in the same subgroup as B, or is in the same equivalence class as B. A disadvantage of this bar notation is that many symbols represent the same element of S. Sometimes this disadvantage can be overcome by choosing a particular element, a representative element, in each equivalence class. So for example, this is what I just said, the even and odd integers are often represented by 0 bar and 1 bar. What did I just tell you? I'm the smartest mathematician who ever lived, and this is what I'm telling you. Are often represented by 0 bar and 1 bar. Even odd is equal to 0 bar, 1 bar. Though the pile picture may be easier to grasp at first, the second way of viewing S bar is often better because the bar notation is easier to manipulate algebraically. The bar notation is fucking stupid. Okay. Equivalence relation defined by a map. This is really, really, really important in fucking topology. Okay, this is really important in topology. Okay, any map of sets F from S to T gives us an equivalence relation on its domain S. It is defined by the rule A is congruent to B if F of A is equal to F of B. Okay, go look in Munkers. look up quotient topology. And maybe I will do a video on this, but I will 100% do a video on the quotient topology. You know what, let me pull up Munkers. Munkers. Do I have Munkers? Maybe in my downloads. This is my memes folder as well, and so there's some spicy stuff here, so I gotta be careful on what I click on. Munkers. Oh wait, it might have a different name. Is it called like Topology? Fuck. Go look in Munkers for the for quotient topology. There will be a link to buy Munkers down below. Okay, pre-image. This is important. So here he's going to give an interesting example. Okay, so the classical example of the quotient topology is the constructing the torus out of the plane. And to do that, what you do is you take, so you can visualize this actually if you have a piece of paper. So you take these two pieces of paper, this piece of paper, and you fold it against itself so that this edge matches this edge. So this side matches this side. Okay, and then you'll get a cylinder. Okay, and so this will be a cylinder. Okay, and then now you can fold it so this edge matches this edge, or this edge, and then you will have a torus. Okay, and that is mathematically how you construct the torus. You actually take the group Q2 or R2 if you're a you take, god damn it, 23, go back up here, 23, 36. Okay. You take the group Q2 and divide out by Z2. So you take all possible rational translations of the plane and you mod out, you say, I am considering the plane, but I don't care about translations by an integer coordinate. And when you do that, the space you wind up with, the pi, so the pi map in this case is from Q2 to Q2 mod Z2. And I think Lang's algebra does a better job of drilling in this point. Lang algebra. And so maybe we'll go read Lang's algebra. That's a really rough book, though. Okay. We go with pi from Q2 to Q2 mod Z2, and that is saying I don't care about translations by integer coordinates, i.e., I now have a torus. And so what happens is, let's say that you have a system of differential equations, okay, and it has two parameters that are both rational or real numbers if you work for the CIA. You have two real parameters that give you the phase space of your differential equation, okay? And phase space means set of possible states, okay? Set of possible states of your differential equation. So a great example, a classic example of this is a pendulum, which is, I'll go over this at some point, but a pendulum is a differential equation, a pendulum with no friction, of course, because you just assume friction is non-existent in physics. But a pendulum, don't quote me on this, I might have this wrong, because differential equations is a weak point of mine. But if you have a pendulum, the phase space of that is invariant under a transformation by integers. So I think the way it works is, let's say you have a pendulum, and it's like this, okay? So it's determined by its position and its velocity. I think those are the 2 points. So if you graph the position, so like let's say the x-coordinate of the pendulum against its vertical velocity, something like that, then, well, oh, no, not x. Let me, not x. You graph the angle, the angular offset. So, sorry. You graph the angular offset, something like this, okay? So this angle is called theta. Well, this is invariant under, if you add 2 pi to theta, so theta plus 2 pi, well, that's in angle logic equal to theta. So at least this has the phase space somewhat of a cylinder. And then velocity, I can't remember. I'm gonna have to refresh on this because now I'm thinking that I might be wrong. But anyway, there's some classical system of differential equations that has the phase space that topologically is a torus. And my point, which is much more important than the specific example, is that oftentimes symmetries, you can have a symmetry in a physical system, and the laws of the universe are given in differential equations. You have a symmetry in a physical system. Symmetries are always expressed using groups. Symmetries are always expressed using groups. And so what you can learn about the topology of the phase space. Let's just pretend it is the pendulum. I don't think it is. I think it's a different classical. It might be the spring or something like that. Mass on a spring, something like that. It's a very simple, basic differential equation. Artin talks about differential equations in one of the later chapters, so maybe he'll get to that. But it's a classic differential equation. It's one of the differential equations 101 courses, and I got a C+ in that course. I sucked at differential equations. It didn't make any sense to me. Okay, but you take let's just pretend it's the pendulum that is invariant. Its phase space is invariant under some group action, and the group is isomorphic, because isomorphism is our definition of equals for groups. Everything is about definition of equals. Our isomorphism is isomorphic to Z2, okay? So the phase space of the pendulum, the set of all possible states of the differential equation, has a symmetry to it, and the group of symmetries, the symmetry means that if I apply that symmetry, it doesn't change the state of it doesn't change what happens as far as the differential equation is concerned, or as far as solving the differential equation is concerned. So if I have this pendulum and I move it to this, so I have a mass over here and I move it to this position, if I rotate it in 360 degrees, as far as physics is concerned, it doesn't care. That's a symmetry. It's something I can change about the system such that the laws of physics don't care. The laws of physics cannot tell the difference between this position and this position plus 360 degrees. Okay? God, I lost my train of thought. Oh, my point is that what you can do is then prove that that system has the topology of the torus. And topology is incredibly powerful because, in a sense, topology tells you so the topology of a space tells you what type of solutions are possible. Tells you what type of vector fields are possible. So let me give you a very simple example. So you might have heard of something called the Hairy-Ball theorem. So what this is that, let's pretend you have a tennis ball with hair. It's impossible to comb the hair on the tennis ball in such a way that you don't have a singularity. what the Harry-Ball theorem formally is that if you have a two-dimensional sphere, so two-dimensional sphere means this, like the surface of the Earth, surface of the tennis ball, and you have a vector field on the surface of a two-dimensional sphere, the Harry-Ball theorem, I believe, states that it is impossible to have a continuous vector field on the surface of a two-dimensional sphere. Vector field means tangent vectors. Okay, so it is impossible to have a continuous vector field on the surface of a two-dimensional sphere that does not have two vectors that are antipodal that are equal. I think this is related to the Borsakulum theorem. But I'm just kind of going based on memory here. Borsakulum theorem. Okay, so a consequence of this is that there are always two places on Earth, or there is always one place on Earth that has no wind. That's the Harry-Ball theorem. There's always one place on Earth where there's no wind. And then if you plot two continuous variables, so you plot, let's say, the wind speed and the barometric pressure, two continuous variables. So the Borsakulum theorem is about maps from S2 to R2. That's right. And this is about vector fields on S2, which is actually the same thing. A vector, they're actually the same thing. A vector field is just a map S2 to R2, because at every point of S2 you're defining a two-dimensional vector, which is a map from S2 to R2, formally. These are the same thing. That's why I had them confused in my head. A vector field and a map are the same thing. Borsakulum theorem is about like flattening a sphere. So, point with the Borsakulum theorem says that if you have any map from S2 to R2, you will always have antipodal points on the sphere that map to the same point in R2. So if you have a map from S2 to a continuous variable in R2, so let's say you go from S2, so the surface of the sphere, the Earth, to, let's say, wind speed and temperature. Doesn't matter. Any two continuous variables. There are always two antipodal points on the sphere that have the same wind speed and the same temperature. And that is a fact of the geometry of the topology of S2. It is forced by the fact that the Earth is a sphere. And it is super weird. Okay, that fact does not hold on the torus. So if you can prove that your differential equation has the topology of a sphere, or it has the topology of a torus, or it has the topology of this, or the topology of that, that changes qualitative properties about the differential equation. That is why this is important. Is that your group of symmetries can change qualitative properties about the equation. Okay, let's just show an example of what he's talking about here. Here the set S bar of equivalence classes has another incarnation as the image of the map. The elements of the image correspond bijectively to the non-empty fibers, which are the equivalence classes. So here is the absolute value map from C star to R star. So this is the length map. Okay, and so here is 0. So what the fibers are preimages of points. So let's say we want all the points that have length 3. Well, this is just a circle. So all the complex points that have length 3, well, this is just the circle of radius 3. Okay? So the fibers above a real number, according to this absolute value map, are just going to be circles. So in a sense, the set of circles around the origin and the complex plane are whatever, equivalent. Okay. These form an equivalence class. So I think Artin's point is that you can use a map like this to partition the original space into equivalence classes. Okay. if G is a finite group, we can define a map F from G to N as positive whole numbers to the set 1, 2, 3 of natural numbers, letting f of A be the order of the element A in G. The fibers of this element are the sets of elements with the same order. Okay, yeah. 2.7.2 was his example with S3. We go back to a group homomorphism phi from G to G prime. The equivalence, so he is hinting at the fundamental theorem of math, which I talk about all the time. So it's related to, what does Spivak call it? Stokes' theorem. It's this theorem that he's referring to, the fundamental theorem of homomorphisms. It's in a sense the same thing as Stokes' theorem. It is the most important idea in mathematics. It is the fundamental idea. That's why we're starting calculus on manifolds. That's why I've been reading that book. Or that's why I read a section out of that book. I want to read that book, but that will take a while. And so I think I will focus on getting through Artin, and then we'll pivot to Spivak. Okay, we go back to a group homomorphism phi from G to G prime. The equivalence relation on G is defined by phi is usually denoted by triple equals rather than by tilde, and is usually called a congruence. So this is the modular arithmetic notation, and I want to here's this equal sign, this triple equal sign. That's the modular arithmetic idea. So, right, I talked about pi from Z to Z mod 2Z, okay, and we write A is equal, triple equals to B mod 2 if pi of A is equal to pi of B, or if the equivalence class of A is equal to the equivalence class of B. All three of these terms, all three of these are equivalent. Okay? We have seen that elements A and B of G are congruent, i.e. phi of A is equal to phi of B, if and only if B is in the coset AK of the kernel K, 2.5.8. Yeah, we talked about that in 25. So we're matching the sections of Artin for a while. Anyway, proposition 56. I just want to see how much time we have left. Oh, we're almost at the end. This is the last section. Okay. This is the last proposition. Let K be the kernel of a homomorphism, G to G prime. The fiber of phi that contains an element A of G is its coset. Right. Right. So the kernel tells you the things that you can't tell the difference between. Right? It's the things that map to 0 down in the downstairs group. Right? So it's saying so what we're saying when we have a homomorphism is I can't tell the difference between point A and point B, i.e. the difference between A and B is in the kernel of the homomorphism. Okay, and I'll maybe give some concrete examples with linear maps. Let me write that down. Concrete, and in Revelations 23, I'm going to do this. Highly anticipate Revelations 23. Concrete examples with linear maps. Linear maps are the homomorphisms in linear algebra. So every theory has morphisms and isomorphisms. These are category theory terms. Category theory is math's version of TV tropes. So morphisms in every field, these have a different term. In group theory, these are called homomorphisms. In linear algebra, they're called linear maps. Oops. ER maps. In topology, they're called homeomorphisms. Oh no, these are called continuous maps in topology. And then when you can invert them, they're called isomorphisms. So in group theory, these are called isomorphisms. In linear algebra, these are invertible linear maps. And in topology, these are homeomorphisms. So homeomorphism means it's continuous and its inverse is continuous. Every theory has this exact same structure. That's why category theory is sort of the TV tropes of math. Category theory is TV tropes for math. Let me write that down. Category, that'll be a block quote for next time. BQ. Is TV tropes for math. Okay, and then the other BQ to add. So this is BQ1 to add, and the other block quote is the 90% of the difference. Because that's going to come up a lot. That's an important block quote to add to the Q. Okay. So, proposition 2.7.5. Yeah, so the cosets of the kernel partition the group, and they correspond to elements of the image, right? Go check out 2.5.8. Go reread that, or go reread the proof for that. And maybe I went over it in Revelation or in AA 25. I went over that. Okay, that's the end of this section. Yeah, so this is a maybe I can draw a better diagram. Okay, so let me draw a better diagram to illustrate this, which is the okay. We have a number line. Okay, and we have our equally spaced points on the number line. So 0, 1, 2, 3, 4, 5. Minus 1, minus 2, minus 3, minus 4, and minus 5. Okay? Okay. So I am going to color these based on even or odd. Okay? So odd ones get pink. Just coloring. That's all we're doing is coloring. Okay? And then even ones, get blue. Okay? And I want you to notice that all of the Y. There we go. I want you to notice that all of the pink ones differ by a multiple of 2. Okay? So we're taking the pink ones and saying our coloring, so our map from Z this is Z to Z divided by 2Z, which is equal to the partition. A partition, maybe you can also think of as a coloring, 0, 1. Oh, that's a much better term as a coloring. Or I think as a better term as pink, comma, blue. This is our partition, and I'm going to also note the blues also differ by an element, by a multiple of 2. Each of these also differ by an even number. So we're taking the integers and we're quotienting out by the even numbers. We're saying, I don't care, we're coloring the integers by whether or not they differ by an even number. And if you have a group of symmetry, so the integers are symmetrized by the even numbers. They're in fact symmetrized by every one of their subgroups, and that's because the integers are an abelian group. Okay, and we'll see this, what I mean by that, when we talk more about abelian groups. Okay, so we have our integers, and the phrase I want you to remember is we are partitioning Z into the orbits of 2Z. And the orbits, by this I mean one of the colors. An orbit is one of the colors. Okay. An orbit is one of the colors. Okay. AA27. That's what we're looking at. Okay? So we're coloring them according to this. And if we do Z mod 12Z, well, we're partitioning them according to which orbit they are in 12Z. So that's the clock arithmetic. That's what's going on here. Okay? I think that this is relatively clear. We're going to see more and more epiphanies in later videos. And I got to edit this now, and I'm annoyed about that. But I know I only have to edit the audio, so at least that's a win. Anyway, I will see you in the next video. Thank you for joining me. I hope you have a nice evening. Good night.